Hey there, I'm Alejandro. Welcome back for day 260 of me doing the Daily LeetCode challenge. That's reach 1 year's worth of Greek contributions here on GitHub. So today's one was for April 2nd, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode easy. Problem 2873, maximum value of an ordered triplet. 1. You are given a zero index integer array nums. Return the maximum value. Okay, so it's an optimization problem. We can usually either use DP, greedy, or divide and conquer. Also, is my brightness is going down. Yeah, everything's at max lighting. Okay, so that's good. Return maximum value of all triplets of indices I, j, k, such that if also triplets have negative value. What? Okay, the value of a triplet of indices is equal to nums of I minus nums of j times nums of k. I see. So I'm guessing that because it's a, yeah, so you can loop, yeah, you can do an n cube solution. Okay, yeah, you want like the biggest triplet, and it's a LeetCode easy because you can write an n cube solution. Okay, well, here it'll be the max of, we can probably do this in one line of Python. Max of, this will be the value. And here we'll say, all right, let's make sure we copy the whole thing. It'll be max of this, y in range, length of nums, for j in range, length of nums, but I must be less than j, so this will be I plus 1 to length of nums, for k in range, length of nums, but k must be greater than j, so this will be j plus 1 length of nums. Something like this. Not quite. Maybe here we can do default equals 0. Okay. Maybe we parenthesize this. Well, okay. One very easy way is max of 0, comma max of everything. And that way it's still one line. There we go. Accepted. Let's submit. And there we go. Bada bing, bada boom. Completion streak 260 days. Consistency is key. See ya tomorrow. And we did it with a beautiful little one-line solution. Okay. So you know what, I can write it as a non-one-line solution, but I'm actually going to do that as I explain my solution. How about that? So nevertheless, as always on my videos, I do a quick recap provided supposed to level problem. So this one, it's actually very easy because, okay, you want to maximize the value over all triplets of indices I, j, k, where the value of a triplet I, j, k is equal to this little formula over here, right? Nums of I minus nums of j times nums of k, right? And so the way that I did this is, okay, here I obviously have one line, but if I comment this out, we can write this in a better way. What I looked first is at the constraints. I looked at nums of length is equal to 100. In LeetCode, you're allowed to do up to 10 to the 6 operations, right? So here, if you have 100, this is really 10 squared. So what you can really afford is if n is equal to 10 squared, right, which n is nums of length, and this is at most 100, which is 10 squared, then n cubed will be equal to 10 squared cubed, which is equal to 10 to the power of 2 times 3, which is equal to 10 to the 6. And we can do about 10 to the 6 operations in LeetCode. Sometimes 10 to the 7, but roughly 10 to the 6, usually you're safe, or a little bit more. So if we have an n cubed solution, then we do at most 10 to the 6 operations, which is completely fine on the LeetCode platform, right? So this makes the problem very simple because here we want the maximum triplet. Computing the value of a triplet is only O of 1 time, and we can just have an n cubed solution, and we will not be going overboard with the constraints over here, which is probably why this is a LeetCode easy. So maybe there's a better way to optimize it, or it's like you do some funky stuff. Let me look at the accepted charts. Okay, there is definitely a way to optimize it. Okay, I should probably try to think about that. But yeah, okay, this is the first solution. But the way that it's solved is like, okay, we're going to go n is equal to length of nums, right? Here we want to go through every single ijk triplet such that it is true that I is less than j less than k. So first of all, let's do for I in range n, right? This makes sense. We're going to loop through every single number. Now we want to do every single ijk triplet. We're going to go through every single possible value of I, so from index 0, index 1, index 2, all the way up to index n minus 1, right? Because here we don't include index n. Now here we'll do for j in range n, right? But it must be that, like, okay, it must be that if I is less than j, right? So it's like, you know, if it's not the case that I is less than j, then here we can press continue, right? And then here we'll say for k in range n, it must be that, you know, k is greater than j. So if it's not the case that, you know, j is less than k, then we shall continue, right? Here I'll do that. Otherwise, here we'll just compute this, right? So we'll say val is equal to this. And here we'll have a result here. Res is equal to 0. Res is equal to, res is equal to max of res, comma val, return res, right? So something like this will work. Yep, and here we can just press submit, right? But this might even be a little bit slower. And here's the reason why. First of all, you know that you want I is less than j less than k. So here what we're doing is like looping through every single possible triplet of ijk, right? So for I in range n, for j in range n, for k in range n, right? Here we can actually do something better, right? We can just say if I is less than j less than k, then and only then we say, okay, we have a new possible candidate, right? So we want all triplets such that this is true. We start with the base of 0, because if all triplets are negative, then return 0. So we start off with 0. And here it's like, okay, every single time we find a triplet where it's like I is less than j less than k, let's compute the value of that triplet, right? The value of a triplet of indices is equal to this little formula over here. So we paste the little formula over here, compute as val, and we'll just set res equal to the max between res and val, and then return res, and then we go bada bing bada boom. We have a nice and efficient solution, right? Now, instead of having this if statement, here we're doing a lot of repeated work. Here we know that for every single j that is not greater than I, then all of these are just gonna be irrelevant, right? So here what we can do is like, okay, only loop through j's that are strictly greater than I, right? So starting from I plus 1 and n. And same thing for k must be greater than j. So only loop through values of k that are specifically greater than j, right? So starting from j plus 1 and n. That way you don't even need this little if statement. You can bring this down, right? And this will still be accepted. And now if you look here on the left, we're over here at, like, you know, 195 milliseconds. If we submit this like this over here, we'll see that we do a little bit of a better job. We are now, I guess, at 163 milliseconds. I guess it's not as fast, but still a little bit faster for sure, right? Here is like, you know, another optimization we can do is like, you know, instead of using max, we can just do if res less than val, then res is equal to val, and maybe this is a little bit better of an optimization as well. Oh my gosh, yeah, definitely. So now we're at 79 ms, beats 50.87% of solutions. So, you know, it's definitely a very nice improvement for sure, right? So just goes to show, like, you know, when you fix the O of 1 stuff, it's kind of nice. But also more importantly, it's like, okay, instead of, like, you know, looping through exactly n cubed, right? This is still an O of n cubed total amount of work, right? But it's similar to how, like, you know, this is like, you know, an n squared amount of work. This is technically O of n cubed still, but it's definitely better than, like, you know, raw n cubed by doing for I in range n, for j in range n, and for k in range n, and only looking at the cases where I is less than j less than k, right? You might as well save on a little bit of work. Now I noticed there's a little peak over here, so this either means that there used to be less test cases, and they got added, or there's a better way of doing things. And since this, okay, this is problem like 2873, I'm guessing like people have just found a better way of doing this. So maybe now, oh, I guess there's hints for this problem. So in terms of the solution explanation, that is pretty much it in terms of how I was able to solve the problem. If you want to stick around here, it's just going to be me trying to essentially come up with a better way of doing this. Otherwise, I'll just leave the problem as is. So, okay, let's think about this a little bit. But yeah, otherwise for the solution explanation, that is literally it. That's all it takes to solve this problem. It's a LeetCode easy because of this. Now I'm just going to spend some time seeing if I can think of doing something better a little bit immediately, right? So here is going to be... Okay, so nums of I minus nums of j. So it's not going to be I minus j, it's going to be nums of I minus nums of j. Nums is not necessarily sorted, right? No. I don't know. Yeah, maybe we could do something like, yesterday was a DP problem, right? So maybe we can do something like DP-ish here. My instinct would be to do something greedy, but this would still be n cubed though. You want nums of j to be small. Oh, I plus 1. Max out. Set the dp of I plus 1. Okay. Set the dp of I j plus 1, comma k. Set the dp of I j k plus 1. Yeah, so that works. Yeah, but no, that is way slower for no reason. It's like, why would you do things this way? This is just dumb. Yeah, so my instinct would be to do something greedy then. It could be that it's one of those where I just had less test cases then. Right, if you do something closer to this edge, yeah, it's like, you'd have to do something based off the formula, right? Maybe it's like I can do a linear scan. I can do my prefix. I want to maximize I, minimize j, maximize k. I can at least try to bring this to n squared if I keep track of prefix maxes and prefix mins, right? I'm pretty sure. Let's try. Nums max less than num, curve max equals num. Prefix max dot append curve max. We'll just say this is nums of 0. here we'll say prefix min is equal to this, cur min, cur min, cur min, cur min, this, right? Printf string prefix max equals, printf string prefix min equals. It's greater than num, cur min equals num. Okay. Yeah, this I probably want to do in backwards order, right? Infinity. Infinity. No. Right. No, I do want to go backwards, right? Yeah, here let's just do this is flow of infinity. Sun. We want to say the max from here is 7. 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 Max from here is 12. So we definitely want to go backwards. Reverse nums. Here we'll just say prefix max is equal to prefix max backwards. Should be just as simple as that. This should be this. Yeah, so now this is 12,777. 19, 19, 19. Yeah, this is just going to be 333. That's fine. Prefix mins. Now this should be. Well, yeah, this is probably going to need to be the same thing. Reversed nums. Prefix min is equal to prefix min backwards. Yeah, what's the next? What's the next? What's the next? Then from this point onwards it's 2. From this point onwards it's 7. Yeah, this is good. Yeah, here it's 1. Then it's going to be 3, 3, 4, 19. This is great. 1, 2, 3. Yeah, this is great. This is great. I'll say for I in range n is equal to length of nums. We need to allow a j and a k index, right? So we're only going to go up to that much. Then we're going to say We have to loop over the prefix max anyways, right? So really, we only need one of these. We only need the prefix max. I was thinking prefix min just for the nums of j parts, but we're gonna have to loop over all the j's anyways, right? Because here we're gonna have to, yeah, the prefix max or prefix min is only gonna be able to bring us down 1 degree, not 2 degrees. If I do I is equal to 0, yeah, because if I have prefix min is like 4 from index 1, I don't know where that 4 is yet, unless I keep track of the index. And I only allow other case, but then I don't know if I'm optimal because I'm skipping things. So I definitely need to still have it for j in range I, all the way up to n minus 1. But now we can say, now instead of adding a third loop for k, we know that we are multiplying. Oh, wait, prefix min is going to be great when we have negative values, because it could be like a negative times a negative makes a positive. So actually, we kind of do need prefix mins. Multiplying nums of I, nums of j, by nums of k. Nums of is greater than 0, we want index k such that k equals max of nums from j plus 1 to n minus 1. Zero no matter what. Hence, we can leverage prefix I, j, k triplets. Right? So here essentially what we'll say is res is equal to 0. Diff is equal to nums of I minus nums of j. Case 1 is equal to diff times prefix max of j plus 1. Case 2 is equal to diff times prefix min of j plus 1 equals max of res, case 1, case 2, and then return res, right? That's what I'm thinking. Hey, beautiful! There we go. That's how we do it, baby. Nice. And yeah, you can't just do this, right? This, because you might have negative solutions. So this is going to be incorrect. A what? That's because they don't have enough test cases. That should not work. That should not work. They do not have enough test cases. 564 though. Jesus Christ. Oh, are all the values positive? Oh my gosh. Edit. Since nums of in constraints, it states that nums of I num in nums is positive, I greater or equal to 1, it can never be that nums of k is negative. Hence, we don't even need the prefix min part. So here we'll say that, yeah. We'll just say max of res is equal to res of j times prefix max of j plus 1. Res less than val, res equals val. And here we don't even need this. Yeah, that's a bit of a rip right there. Okay, it's taking forever. Okay, but wow, yeah, now we have 3MSB78. 0.55% of solutions. Maybe we can do some things a little faster. Yeah, here we could just do n minus j. And maybe that's a little faster right there. Uh, 0, 1, 2, 3, 4. Maybe it's like -1. Maybe we have a +1. Yeah, let's see. Maybe it's, okay, so this is failing. Maybe this is a +1. Otherwise, I'll just bring it back to what it was before, which is this, and just j plus 1, because that makes life easy. Maybe we say collections.deck. Maybe we just say append left. That actually makes this a little bit slower. Darn. If I want the ith index, right? Right? If I have nums from 0 to n minus 1, and there's n minus 1 minus, there's n minus I total indices here. -1. Negative. Negative n minus this, basically. That should be fine. No. Okay. Otherwise, I just don't bother. I mean, at least in terms of asymptotic complexity, I have an optimal solution. Yeah, it is what it is. Yeah, but at least we're now, we're obviously in that peak now. Yeah. Which do be quite nice, not gonna lie, not gonna lie. Yeah, we can get rid of this. Yeah, this is fine. Anything I can do better? Yeah, I can probably, like, I mean, even if I do this part, nah, this part is not going to be the thing that makes it end all be all, right? It's the fact that I'm doing n squared work over here. Like, is this really faster if I do this? Yeah, not really, right? Yeah. I mean, yeah, this is what it is. I don't think I'm gonna get 0ms speeds 100% solution, but it is what it is, right? We're obviously right at the standard deviation peak. So yeah, in case you're still watching, like, as a second little solution here, essentially the way that you can transform this into n squared time instead of n cubed time is by realizing that, like, hey, so since this is this little formula, right? Here you can loop over every single pair of indices I and j, such that, well, like I is less than j. But oh, first of all, here I can just do this. Holy crap, I completely messed that. I can just ignore those. Okay, so now I'm at a nice 3% 3ms. Yeah, I should definitely ignore those because, well, okay, maybe that's a little misslip on their end in terms of the test cases not being comprehensive enough. But the point is, essentially, you can cut down on the looping for each k part, right? So here you still do of n squared work to loop through every single possible indices of I and j where I is less than j. But then it's like, okay, you know that you're going to multiply your result by nums of k, right? And nums of k can only be a positive value, right? So you can only magnify whatever this value is, right? So if it's negative, then you know that you're going to drop negative values and make them zeros anyways, right? Before, what I was doing is essentially I was keeping track of prefix mins as well. That way it's like, okay, if this thing is negative, then essentially we can multiply by negative nums of k, which make it like, mega positive and so on. But here, since the constraints say that all the numbers are positive, we can actually just scrap the prefix mins, which is why I commented them out, to essentially just say like, okay, this can only magnify an effect, so it can only make things like, either more negative or more positive, right? We know that anything that is negative is essentially going to become a zero anyways. So when we start at 0 and so on, if we have a negative thing and so on, doesn't matter, it'll be 0, so we essentially don't consider it. Otherwise, if that nums of I minus nums of j is positive, then essentially we want to multiply by the maximum possible nums of k that we can have, right? We want to make it as big as possible. So we might as well keep track of a prefix max array where prefix max of I is equal to max of nums from I That is essentially what prefix max gives you, and the way that we go through that is essentially we start from the very end of the array, and we say, okay, the maximum index from the last one is going to be 7. The maximum one from this index is going to be the max of 2 and 7, which is just 7. The maximum from this index is going to be the maximum between 1, 2, and 7, which is just 7, right? But the point is that as we keep doing these maxes from the right, we're not actually comparing 3 values. We're comparing the max between 1 and the previous max we've computed before, which is the max of 2, 7. When we do it for 6, it's like we've already computed the max of 1, 2, 7, and 7. So then we do max of 6 and 7, and that just happens to be 7. Then we do max of 12, and what we computed for here, which is a 7, so max of 12 and 7 is just 12, right? And so we'll end up having a prefix max array that's just like, well, when we reverse it, it'll be 12, 7, 7, 7, 7, right? So essentially, prefix max at index I will give you the value of the maximum number from index I onwards inside of nums, right? So then what we can do is like, okay, for n range n all the way up to n minus 2, because we need to allow up to 2 more indices for the j and the k. Then for j, starting from index I plus 1, so that it is greater than I, but all the way up to n minus 1, because we need to allow at least one index left for the k element itself. And then what we're going to say is like, okay, we know that, first of all, if this is negative, then essentially we're going to scrap this case anyways, right? So we might as well multiply by the largest value of k that we could possibly have. Doesn't really matter. It's going to be negative at the end of the day. So when we say if res is less than val, we will not trigger the set statement because it'll be a negative value, and res is already 0 by default, so we will just ignore it, right? Otherwise, so that basically means we can pretend that without loss of generality that this number is positive, which means we want to make it as big as possible, right? So we know that we've locked in indices I and j. Now we need to look at indices of k that is larger than j, right? Which is also transitively larger than I. So here, prefix max allows me to look at the maximum index in nums from an index I onwards, right? Prefix max of I. So here I need to look at only for indices of k that are larger than j. So I can look at any index starting from j plus 1 and onwards. So here I'm going to do prefix max of j plus 1, because prefix max of j plus 1 will be the largest number in nums starting from index j plus 1 onwards, right? J plus 1 or any other index onwards is definitely going to be bigger than index j. So it will be a valid value for nums of k. So we can just multiply by the maximum number inside of nums from index j plus 1 onwards. But since we did O of n work to set up prefix maxes, looking this up is just O of 1. So now we have an O of n squared loop that only does O of 1 work in this body, so it's like, O of n squared in total, which is much better than our original O of n cubed solution. And every single time we just update res if the current value we're looking at is bigger than res, then we return the res at the very end, and there we go, bada bing, bada boom. We have a nice and efficient solution, especially as compared to before. So 8 milliseconds, 3 milliseconds, we're at least hovering down wherever the standard deviation is. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful and enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.